How many participants are there now, Kanfu? Can we start?
Ma'am, we can
Uh,
wait for another couple of
yeah, I
minutes.
guess,
Yeah,
yeah, we should
because
wait for a few.
quite a few of our regulars are yet to come.
Okay, we'll wait then.
Yeah.
But you can take, because recording is already
Huh.
started, please take feedback.
Yeah. Costa, we were
Um,
saying something. You've written something in the chat. It will be good if you speak that. In fact, Kaustubh has been absolutely a regular bacha, and invariably, if I may say so, he's the first one to join. Am I right? In the
Yeah,
last 3 or 4 sessions, he's the first one to
yeah.
come. Yes, Urjit has raised his hand. Yes,
Yes,
Urjit,
Urjit.
would you like to say
Yeah,
something?
ma'am. Ma'am, all the sessions were really great because first off, we started off with the basics and then we further built upon it. So that was the best part because it was really easy to understand because we had started off with the basics and then we moved to the advanced.
I totally agree
Thank
with
you.
you. These three children, they'll make, I was just telling them in the morning, like they do have an alternative career waiting for them in case they want to get into the field of education.
why
It's
not?
been
Why not?
it's been a really good learning experience also, even for me from these children. Like the kind of patience that they have exhibited, the kind of you cannot sustain a 4 week long, twice a week meeting unless and until you have a passion and real interest, deep interest in what we are doing. So that's commendable.
Absolutely, absolutely, Rachna ma'am. And no, I was so convinced after seeing Panthu replying on YouTube, on you know, without meeting him, the very first session of particle physics demystified. Yeah, and he was like going crazy to answer questions, and he was trying to convince then and there. And if somebody is not understanding, reiterating. And obviously, Devangi also. I mean, she was always ready to help. Rachna ma'am, can we take one or two more feedback till students come? Maybe
Absolutely. Yeah,
Arnav,
yeah.
Urjit has
Huh.
already. Okay.
Yeah, anybody else would like to say something? Ananya, you'd like to add something? Samaya? Arnav?
Ma'am, I think
Most
Yeah.
important, whoever is speaking, please switch on your video because it will be there on YouTube forever, and you will feel great. Maybe after a month or when you big and you go to YouTube and say this. Hey, when I was in this grade, I did this course and it was amazing. So please switch on your video when you speak.
Yes, Arnav, you were saying something, Beta?
Yeah, I think I'll just switch on my camera in a couple of minutes. I'll take a bit of time. But I think one of the things I liked was that this was firstly completely beyond what is taught in the school or what is even there in the curriculum. And also, I think there's a lot of content out there on YouTube or online courses from which you can learn. But the great part was that when you have a class like this, you can ask your questions and get all your doubts resolved on the spot. So I think that was a great experience for me, and thank you so much, all the mentors, for this.
I totally agree with you, Arnav. Absolutely.
We would also like all this written feedback. It will be you can say Guru Dakshina to all three student mentors, Arnav. So Arnav, Madhav, and Ujit, whoever has spoken what. When ma'am, Dashna ma'am or Uday share the spreadsheet, maybe after 4 5 years or that will be a record, and these teacher mentor, student mentor will feel great about it. So it will be great if written feedback, one or two line only, can be given. Thank you. Over to you, Pantu, then, and Rashna ma'am and Devang.
I think we can begin now, ma'am. Do we do that? 6 8 हो गया?
Yeah, sure, sure.
Yeah.
Okay. Okay, so welcome to the last session of Fundamental of Particle Physics. It's been an interesting journey. It's new for all three of us also. So it was fun. So first, we'll start by discussing the quiz. There were a few questions that I like. There were a few doubts. So I'll first share the quiz. Wait a minute. Is the screen visible?
Yeah.
Yes.
Okay, cool. So for this question, which of the following are valid types of star? What do you think is the answer is? Anyone? Yeah, go on.
Red giant and white dwarf.
Okay, good. These two, red giant and white dwarfs, they are the valid types of stars. What is the typical mass of a white dwarf?
0.8 to 1.4 solar mass.
Exactly. 0.08 to 1.4 solar masses. This one, 0.08 to 8 solar masses, this 8 solar masses is would be the mass of the entire star. So, a 8 solar mass star would produce a white dwarf which is 1.4 solar masses. So, we have asked the typical mass of a white dwarf, not the star it initially was. So, the answer would be this. Uh, select the points that are true. What about this? Anyone?
Kostov says the first one.
No, the first one is not true. White dwarf cannot perform stellar fusion because they are dead stars. They don't have any more fuel in them. Um, the white dwarf, the star, is entirely made up of your molecules which are very densely packed, so they cannot perform fusion. The actual answer would be the two of these. I did notice that I by mistake I actually did not mark this one as the right answer initially, but don't worry, I'll mark them accordingly according to the new one. So electrons in white dwarf, electrons generate pressure to keep it stable. Yes, the electron they occupy all the velocities that it can, so that and by that it generates a pressure which stabilizes the gravitational force, and that's how it's stable. And white dwarfs have the strongest magnetic. Okay, sorry, this was also wrong. I realized this now. Sorry, I'll correct this question. Everybody will get a marks. Um, okay, next question. What is the Chandrasekhar limit?
1.4 solar masses.
Exactly. And select the points that are true. What about this one?
Every
Any-
black hole has an event horizon. And the last one also.
Yeah. So these two are right. Okay, cool. Good. So I'll stop sharing now. Uday, you can take on and give the briefing.
All right. Thank you. Thank you for that. And yes, good evening, everyone. I hope you all are keeping well. Um, as Franz also mentioned, it's very exciting and also slightly upsetting that we've reached the end of this more than a month-long journey that we took into learning particle physics in more detail. And right now, I'd just like to give you a small recap of everything that we have covered through this journey so far. Before that, I see Dr. Kenji has also joined us. So welcome, sir. Thank you so much for being with us today. For those of you who don't know, Dr. Kenji, along with Dr. Arindam, was were the people who initiated this journey by conducting the first session called Particle Physics Demystified in association with Nucleus. And based on that, we branched off and created this program for you. So we're honored to have you again on the last session. So it seems like a full circle. Now, just to give you a brief recap of everything that we have done in this session so far. So firstly, we started off with the idea of an atom. So in the first session, we discussed what an atom is, why we started thinking about the atomic model, and we discussed how through different atomic models and different ideas, we ultimately reached the electron cloud model and how we started going deeper. And we also tried to get further into what lies inside an atom, which is where particle physics started shaping up. After that, we delved into the standard model, which is a description of the universe and everything that makes up the universe, so all the fundamental particles that we know of. We talked about those in our sessions on the standard model. After that, we also discussed the fundamental forces, where we talked about the four fundamental forces that govern the universe and all the interactions that take place, and how these can be explained or not be explained using the standard model. And after that, we also talked about the Large Hadron Collider at CERN, and how scientists and particle physicists have been using these large feats of engineering to figure out more about what the universe is made up of. Then, of course, we also talked about what these particles, the fundamental particles, actually are. So we talked about what quarks are, what leptons are, what the Higgs boson is, what the neutrinos are, and so on. And we also talked about what antiparticles are. So these were some topics that we also covered. And after that, we delved a bit into astroparticle physics, where we started talking about how do these particles actually shape up the universe. So we talked about what stars are, how many types of stars exist, their life cycle, and how they go through birth and death, and how they pass through different stages in their life. We talked about concepts such as stellar fusion, in which stars fuse different materials inside their cores to give out energy and continue with their lives. Then we talked about the death of a star, where we talked about what a black hole is, what neutron stars are, and what white dwarfs are. So we tried to give you a deeper understanding of how things in the universe actually go through our life cycle, and how they meet their end, and what their ends actually mean for the universe. And lastly, the topics that we will be discussing today are some of the topics that none of us know about. And by none of us, I don't mean the three of us, I mean humanity as a whole, I mean the scientific community as a whole, which are dark matter and dark energy. So this is the last frontier of particle physics, because we are actually reaching topics that we haven't understood completely. So we're talking about the limits of the standard model and particle physics, and we're talking about how there is a lot of stuff in the universe that we don't completely understand yet. So these are the bits that we have discussed in the past. If any of you want to catch up at any point in the future, as we have mentioned earlier as well, all of the sessions are available on YouTube and on the Nucleus website at all times. So if you ever feel like you need to catch up on all the topics that I mentioned, you can go back and talk about and cover and look at those once again. And if you ever feel like you are in doubt about any of these topics, you can feel free to write to us as well. So that was a brief recap of what we have achieved in the past 1.5 months, and I hope that we reach a good closure today as well. So I'll hand it back over to Panto, who can take us forward with today's session.
Krishna, would you like to have any announcement for the learner?
Children, it will be really nice if you can switch on your cameras. This being a very important session in many ways, so kindly switch on your cameras.
Yeah. The students, especially.
Devangi, Samaya, Madhav, Arnav, please switch on your cameras.
In a relaxed mood, but it's good if some of you switch on your camera, because you'll be, yeah? Okay, so please take it for Panto. That's great, Urje. Few of you have also switched on. It's good. Thank you.
Okay, so we first talk about what is baryonic matter. All the matter that we have discussed till now are called baryonic matter because they're made of baryons, that are protons, neutrons, electrons, and their subparts, and everything is baryonic matter, be it galaxies, stars, Earth, black holes, nebulas, supernova explosion remnants, white dwarfs. They're all baryonic matter. Now, this is an important term because, next slide. Because when we look at the energy distribution of the universe, ordinary matter or baryonic matter is only 4.9% of all the energy that is there in the universe. 26.8 is dark matter, and 68% 8.3 is dark energy. And also one more thing, that is baryonic matter is matter that interacts with light. The matter you can see, it gives off photons and all. So yes, so this is a very puzzling truth that was discovered by cosmologists. Well, there were a few who tried explaining this, but basically when they looked out into the universe through telescopes and calculated the mass of galaxies and all, they found that it's not enough. Like what we see, it's not enough. Okay, next slide. Okay, so next question is, dark matter is something that we cannot see. Nobody has seen. Even our instruments, experiments, they can't pick on it directly. So how do we know dark matter exists? So there are basically two main scenarios where dark matter is the answer to the problems. One is the rotation of the stars around a galaxy. So according to rotational mechanics, the stars should be flinged into intergalactic space because there just isn't enough gravity from normal matter. The galaxies are just not massive enough. Experimentally, we need about 10 times more mass in our Milky Way only to prevent this. Now, for example, in this graph, the basically from the center of the Milky Way, if you go, or any galaxy, um, the stars at the exact center will have a low rotational speed because is not much of mass. There's only the black hole which which gives off the mass. But as we go beyond that, you get more mass, you get the other stars, you get gases, you get nebulas. So as the mass increases, the velocity of the rotation should also increase to a point, because after that point the distances become too great that the gravitational pull actually decreases. So they should ideally fall. This is what the expected graph says. It increases to a certain point and then it goes down, because that's what we expect. So the stars at the end of the galaxy should be moving much slower than the gases in where the maximum should be. But this is not we observe. When we observe the rotations of different stars, it more or less stays the same no matter where you see. In fact, in a few cases, it increased. The velocity of the stars as you go further from the galaxy, it increases, which was very puzzling because according to every law, every physics that we know, be it relativity, be it classical mechanics, it should not happen. So there, at this point, when they did this graphing, they knew that something is missing. The galaxy is just not massive enough for this. So after this, they from this observed result, they tried to see how much matter would the Milky Way need, and they saw that it needs at least 10 times more mass, which is puzzling because like that's a lot of mass. But this, and certainly you can't, and certainly it's not missing from the galaxy. So here we knew that something is wrong. Our understanding of the matter of the universe is not complete yet. Next slide, please. The second point is gravitational lensing. So according to general relativity, light can be bent due to gravity. It also happens near the black hole. Remember, in the last session, I talked about near the black hole, light revolves around the black hole, creating a photon sphere. Similarly, and that's also because of gravity. So gravity can bend light. So now, if there is a massive object in front of a galaxy, like a galaxy cluster, a cluster of galaxy, in between you, the observer, and another galaxy that you are trying to observe. If there's a galactic cluster in the middle, the galactic cluster has a lot of mass. So then a lot of energy also, a lot of gravity also. So this massive object behaves like a lens. What a lens does, like the light from the distant galaxy is coming towards us and it passing towards the galactic clusters, and on that, and while passing through the cluster, it bends the light so that it comes at an angle to us. That's basically what happens at a convex lens. And what does a convex lens do? It magnifies it. That's how we can actually see a lot of galaxies, which ideally we should not be able to see, because galactic clusters, they magnify other galaxies. So this happens. In fact, this picture that you see is that ring around is a distant galaxy, which is distorted by the elliptical galaxy in the middle. It's a huge elliptical galaxy, and the ring that you see is a much farther, smaller galaxy. But due to gravitational lensing, because it's just in between of the light rays, the whole galaxy comes out very distorted. So experimentally, we know that most of the galaxies are not massive enough to produce this level of distortion. Hence, the mass is coming from something else. Here also we see that the galaxies of the mass is just not enough. In fact, gravitational lensing has been seen through empty space. Like we know that there are no galaxies or galactic clusters or anything. There can be a bit of your gases, diffused gases, but they're not massive enough for this. So, but still, through empty space also, we have seen that in a lot of cases, we have seen gravitational lensing through empty space. Again, now we know that it's not, we don't have enough mass. So after this, we knew that there's something else. There's a dark matter which exists in this universe. Next slide. Okay, so what we know about dark matter? We know that it is not normal matter that we cannot see. That is, it's not your brown dwarfs or black holes or neutron stars. We do not produce lights. It's not asteroids. It's not random planets floating around in interstellar or intergalactic space. We know that because, again, it won't add up to that much. We know it must be cold and slow moving, even in the early universe. So cold is like cold basically says that it has less kinetic energy, and if it has less kinetic energy, it's slow moving. That is, it can clump together. If it was fast moving, then dark matter, like we see dark matter in lumps. Indirectly only, we see dark matter in lumps. If it was fast moving, then we would see that that lump is moving, or honestly, the lump would never even have formed. So we know that it is cold and has to be slow moving, and it should have been like this in the early universe also, when everything around was hot. Dark matter must not react with much with normal matter or even light. We know this because our galaxies don't react with dark matter. We can't see dark matter, and because of that, we can safely say that it does not react with our normal matter or even light. And light does not only mean visible spectrum, but everything, your gamma rays, x-rays, infrared, everything is light. So it does not react with our gluons and all. So it does not react with the gluon field, the bosons, or even photons, that is light. Dark matter's effect are most dominant on average in the smallest of galaxies. Again, a larger galaxy still has a bit of mass. For example, experimentally it is seen that for smaller galaxies, smaller than the Milky Way, it is seen that sometimes the ratio of normal matter, baryonic matter, to dark matter is somewhere between 1 is to 5,000 times. That is, the dark matter has to be 5,000 times the mass of the actual smaller galaxy. In case of Milky Way, which is a big type galaxy, almost on the bigger side of the spectrum, it's around 10 times. The dark matter is 10 times the observed amount. So we know that the reason these smaller galaxies can exist is, again, because there is a lot of dark matter. We don't know how and why is dark matter there. Intuitively, the dark matter should clump with the bigger material things, the bigger galaxies, because gravity. But this is not what we see. And then it causes gravitational effects in place where normal matter isn't located, like gravitational lensing through empty space, or even when we zoom out in a galactic cluster level, there are voids. Those voids are somehow stable, and a lot of time the voids are stable because there's something in it. Or if it's really just empty matter, then your normal matter should diffuse into them. But in a lot of galactic voids are stable, so there must be something there to make it stable. Next slide. So now, what we don't know about dark matter, we don't know what particles are responsible for dark matter, or if it's even a particle. Yes, Vidush?
If there is dark matter inside void, then then why do we even call it a void anymore?
Because it's a theory, and also we call it a void because it's not normal matter. We can only call, like, we are only calling this the void and all because we have seen that it does not have normal matter in it, that baryonic matter. There's no galaxy, there's nothing. So it's a theory that the voids might have dark matter or must have dark matter to make it stable. So it's basically we cannot see dark matter, or we can't measure anything about the dark matter. That's why it's not considered very much like matter. Yes, Urjit?
So, is there actually a way to identify the presence of dark matter on Earth, for example?
On Earth, typically we don't see any dark matter, like influences of dark matter, because everything that in the solar system, anything that moves or can be explained by classical mechanics, or like your classical gravity, Newton's gravity, or sometimes Einstein's gravity, for example Mercury. We have not seen any discrepancy in there, any kind of gravitational discrepancy. Like for example, if we saw that like with distance, the gravitational pull decreases with respect to 1 by r and not by 1 by r square. I talked about that gravitation follows the inverse square law. That is, it decreases with the square of the distance. But if it decreases with the distance and not the square, we could have said that yes, the dark matter exists in our solar system. But we simply cannot say that because everything more or less just fits Newton's gravity or Einstein's gravity. So on Earth or in the solar system, or even in most in most star systems, we cannot say that dark matter plays a huge role. But when we look at this cluster of stars, we can there's some things can be attributed to dark matter. For example, stars also influence other stars while moving, right? So there might be stars which are influenced by our sun and it's coming towards us, or maybe we are pushed back by another star because of some gravitational pull. So in that cases, in some cases we have seen that the star might need more mass than it usually has. For example, if we look at the sun star system, only the local cluster of our stars, the sun should have at least twice the mass than it has currently. So that twice of the mass might be a mathematical problem, or it might be dark matter. We don't know where the dark matter is. In our solar system, we don't see any evidences of dark matter. So there's that. Urjit, does this answer your question, or am I missing something?
No, no, no. Thank you for that.
It's okay? Okay. So coming back to this slide, we don't know if the particles are simple or have a rich variations like normal matter. Like we don't know if dark matter has particles or is it just blobs floating around in space. We don't know if it has particle. We don't know if it's just simple, maybe one particle or two particle, or maybe it has a rich diverse types of particles like the standard model that we see in a normal matter. They're like six quarks and leptons and all. They're all different types of baryonic particles. We don't know if the dark matter particles are maybe simple, or maybe they have a rich classification like that. We don't know if the dark matter existed in the universe or something else created it later. We don't know if it was created with the universe initially, or maybe it was in when the universe was born. We don't know if it was created in the Big Bang, or maybe something just happened and it started forming later. We don't know that. We don't know if the dark matter is stable, eternally stable, or will it decay away eventually. Maybe it decays away into normal matter. Maybe dark matter is just a more sophisticated, more complex version of normal matter. We don't know yet. If it's eternally stable, then we might never know. But if it decays, then maybe one day all the dark matter will just decay into normal matter. Will we ever be able to detect dark matter directly? Because everything that we use to detect dark matter is like we can detect using our instruments is light, is the fundamental forces or anything. The only thing that the dark matter exerts is gravitational just because it has mass. Yes, Arnav?
If dark matter exists and if it decays, will there be any observable effects?
We don't know that. Maybe it decays into more complicated dark matter, or maybe again dark matter. If dark matter has a rich spectrum of types, that is, like for example, quarks, the top quark decays into up quark. For example, like if there's dark matter counterpart. So, for example, there's a dark matter particle which is similar to an top quark, and it decays into smaller, more stable dark matter particles. If that happens, then we won't know, because again you get dark matter and it decays into dark matter only. But if, for example, maybe dark matter is was formed from normal matter due to some process that is not possible anymore, or we don't know yet. If dark matter decays into normal matter, maybe then we'll be able to find out, but we don't know yet. So yeah, does that answer your question?
Yeah, thank you.
Okay, so will we ever be able to detect dark matter directly? Like everything that we use to detect things or experiment with are the fundamental forces, are lights, are like these, mostly photons, but they don't detect. But dark matter does not react with these. So maybe we people who are normal matter people might not ever be able to detect dark matter directly or ever use it, because we won't even know it's there. So there are a few questions that we don't know anything about the dark matter yet. Okay, the next slide, please. There's a video, we'll watch it, which is about dark matter and dark energy.
Matter, as we know it. Atoms, stars and galaxies, planets and trees, rocks and us. This matter accounts for less than 5% of the known universe. About 25% is dark matter and 70% dark energy, both of which are invisible. This is kind of strange because it suggests that everything we experience is really only a tiny fraction of reality. But it gets worse. We really have no clue what dark matter and energy are or how they work. We are pretty sure they exist though. So, what do we know? Dark matter is the stuff that makes it possible for galaxies to exist. When we calculated why the universe is structured the way it is, it quickly became clear that there's just not enough normal matter. The gravity of the visible matter is not strong enough to form galaxies and complex structures. Stars would more likely be scattered all over the place and not form galaxies. So we know there is something else inside and around them. Something that doesn't emit or reflect light. Something dark. But besides being able to calculate the existence of dark matter, we can see it, kind of. Places with a high concentration of dark matter bend light passing nearby, so we know there's something there that interacts with gravity. Right now, we have more ideas about what dark energy is not than what it is. We know dark matter is not just clouds of normal matter without stars, because it would emit particles we could detect. Dark matter is not antimatter because antimatter produces unique gamma rays when it reacts with normal matter. Dark matter is also not made up of black holes, very compact objects that violently affect their surroundings, while dark matter seems to be scattered all over the place. Basically, we only know three things for sure. 1. Something is out there. 2. It interacts with gravity. 3. There is a lot of it. Dark matter is probably made up of a complicated exotic particle that doesn't interact with light and matter in a way we expect, but right now, we just don't know. Dark energy is even more strange and mysterious. We can't detect it, we can't measure it, and we can't taste it, but we do see its effects very clearly. In 1929, Edwin Hubble examined how the wavelength of light emitted by distant galaxies shifts towards the red end of the electromagnetic spectrum as it travels through space. He found that fainter, more distant galaxies showed a large degree of redshift. Closer galaxies, not so much. Hubble determined that this was because the universe itself is expanding. The redshift occurs because the wavelengths of light are stretched as the universe expands. More recent discoveries have shown that the expansion of the universe is accelerating. Before that, it was thought that the pull of gravity would cause the expansion to either slow down or even retract and collapse in on itself at some point. Space doesn't change its properties as it expands. There's just more of it. New space is constantly created everywhere. Galaxies are tight-bound clusters of stuff held together by gravity, so we don't experience this expansion in our daily lives, but we see it everywhere around us. Wherever there is empty space in the universe, more is forming every second. So dark energy seems to be some kind of energy intrinsic to empty space. Energy that is stronger than anything else we know and that keeps getting stronger as time passes by. Empty space has more energy than everything else in the universe combined. We have multiple ideas about what dark energy might be. One idea is that dark energy is not a thing, but just a property of space. Empty space is not nothing, it has its own energy. It can generate more space and is quite active. So as the universe expands, it could be that just more and more space appears to fill the gaps, and this leads to a faster expanding universe. This idea is close to an idea that Einstein had back in 1917 of a concept of a cosmological constant, a force that counteracted the force of gravity. The only problem is that when we tried to calculate the amount of this energy, the result was so wrong and weird that it only added to the confusion. Another idea is that empty space is actually full of temporary, virtual particles that spontaneously and continually form from nothing and then disappear into nothing again. The energy from those particles could be dark energy. Or maybe dark energy is an unknown kind of dynamic energy fluid or field which permeates the entire universe but somehow has the opposite effect on the universe than normal energy and matter. But if it exists, we don't know how and where, or how we could detect it. So there are still a lot of questions to answer. Our theories about dark matter and dark energy are still just that, theories. On the one hand, this is kind of frustrating. On the other hand, this is frontier science, making it very exciting. It shows us that no matter how much we feel we're on top of things, we're still very much apes with smartphones, on a tiny fragile island in space, looking into the sky, wondering how our universe works. There is so much left to learn, and that is awesome. This video is supported by the
Anyone have any questions regarding dark matter? Because after this, we'll be shifting to dark energy. So you can ask questions regarding dark matter if you want. Well, okay, then over to you, Devangi.
Oh, yeah.
matter as we know it.
Okay, so from the video, I'm sure you have some idea about what dark energy is. It is a hypothetical form of energy. It is, we can say it's opposite to gravity, since like gravity, it pulls everything together. Dark energy kind of just, it has a negative impact on matter, or like it has a negative impact of that of gravity, and it makes up almost 68% of the total mass energy of this universe. And like dark matter, dark energy is also not directly observed. We cannot see dark energy or we cannot feel dark energy, but we know dark energy exists because we have seen, because of observations made from astronomical objects, right? So one of the main things that shows that dark energy exists is because the universe is expanding. So we know that the universe is expanding. So what we mean when the universe is expanding is that the space between the galaxies or the clusters of galaxies is expanding. and this expansion, it speeds up with time. That is, the expansion is accelerating, it is not constant. um, Back, Albert Einstein thought that universe was static, but that is not true. In 1929, Edwin Hubble, he discovered that universe is expanding. So he observed that the space between two galaxies was increasing, and as the galaxies went further apart, the speed at which they were expanding kept increasing. But it was kind of not expected for that to happen, because due to gravity everything would be just pulled in together, and it was expected that the universe would slow down, because what gravity does, it pulls everything together, right? But that did not happen. So one of the explanations for this is that there's something known as dark energy, which has an opposite effect from gravity, and therefore it helps the expansion of the universe. Any questions about this? Okay. Uday, would you take over?
Yeah,
Yeah.
I think
Okay.
you just have a question.
Yeah, I just had a very small question. So, so if you compare the net effects of all the forces that are happening, as in gravity and dark energy, so which is actually dominating or overpowering? Because due to dark matter, I guess gravity can be there, and that can help us to actually see that gravity is exceeding the net amount of force exerted by dark energy. So, can that be a point?
Well, we
So
don't. Yeah. Go ahead.
yeah, should I go ahead?
Yeah. Yeah. Sure.
Okay, so yes, you're right. Dark matter has gravity. So ideally, everything should be pulled, right? Pulled, and the universe should like go back and like it should decrease. But as we know that the speed, the acceleration of the universe is increasing. The speed at which the universe is expanding is increasing. We know that the counter gravity force, which is caused by the dark energy, is more. Basically, in physics, when you have to see which is the net force, in this case, gravity is pulling everything towards the center, towards something, each other, and dark energy is pushing everything away. And now that we know that it's happening that way and it has an acceleration, we know that that the dark energy exceeds the dark matter, the gravity caused by the dark matter and Barionic matter combined.
Right.
So
And
yes, in
since
the
dark energy has like the most amount of percentage, right? Because dark energy is almost 68 to 70%, whereas dark matter is all like it's very less than dark energy, which is 25. So even if dark energy does have gravity, does like react to gravity, dark energy still, sorry, dark matter, dark energy still is more in abundance. So it can be more overpowering.
I'll just add one more thing, that when you're comparing gravity and dark energy, you have to keep in mind that the scale that we're talking about. So, firstly, when we're talking about uh, gravity, right, the Newtonian formula for gravity is F is equal to gmm by r square. So, gravity follows the inverse square law. That means it's distance dependent. So, you would see that if you talk about two close by galaxies, for example, the Milky Way and the Andromeda galaxy, you would see that here between these galaxies, instead of the Milky Way and the Andromeda being torn apart because of dark energy, they actually are they are continuing to come closer to each other, because gravity is able to overpower dark energy, because the distance between these two galaxies is not that much, and because gravity is dependent on that distance, it's able to overcome the force of dark energy. That's why Milky Way and Andromeda are still coming together. But when you look at dark energy, we don't know if it follows the inverse square law, and it probably doesn't, because it's uniformly spread out throughout the entire universe. So we know that whatever is causing dark energy, it's spread out everywhere. So if you look at the largest scales of the universe, like the literal cosmic scales, like the huge voids between galaxies, there you would see that the gravity does not have any effect on dark energy, because dark energy simply overpowers gravitational force, and everything seems to be moving away from other entities. So you can think of it that way.
Yeah,
Does that
thank
answer
you
your
for that.
question? Okay.
Divangi, can you move to the next slide, please? Yeah, thank you. So in the video, we before this, if anyone has any more questions, or should we move on? Okay, we'll move on then. So in the video, they talked a bit about redshifts. So before I explain what redshifts are, I would like to explain what the Doppler effect is, which will allow you to understand what redshifts are on its own. So I don't know for sure, but you might have heard of the term Doppler effect being thrown around here and there. It's not something that's exclusive to particle physics or astrophysics. It's something that we observe anywhere. So a very common example is, let's say you're sitting in a car, and another car is moving past you, or maybe there's a bike moving past you, which someone is like has his hands on the horn as it's going by. So you would see when the bike goes by you, you hear the bike, but in a peculiar fashion. So you don't just hear the horn go, you hear the horn in a different way. So it goes, "Ping." I'm not a very good demonstrator in this way, but I'm just trying to give you an idea that you see that when it's passing by you, you hear it at a lower pitch, and when it goes away, you hear it at a higher pitch. The same is also true for trains. So let's say you're sitting in a train and you see someone moving by you, and not someone, you see a train moving by you. So you would hear the train coming from another direction in a specific pitch, and as it goes ahead, you would hear the pitch change, right? So that is called the Doppler effect. Why does it happen? It's very interesting. So whenever there's a wave being emitted, like in the case of the train and the car, we're talking about sound waves, right? Because we're talking about hearing things, which is caused by sound, and sound, as you know, is a wave. So when we're talking about waves, we are looking at waves being emitted from a particular source. So in the case of the bike, let's say, the bike horn becomes the source. So let's say if I say that this bottle right here is the horn, and I'm standing here, then the horn would start emitting a certain wave, and I would be perceiving it right here. So I would be perceiving the same wave continuously without any changes, right? Because I'm not moving, and the object is not moving, and I'm continuously getting the waves thrown at me, right? But let's imagine if this particular horn is moving in front of me, or you can also refer to the diagram over there, where the source is actually moving towards the right. So what happens is, as the direction of, or as the source changes positions, the frequency at which the wave is received would actually change. So again, if this bottle was emitting a wave, it would be emitting the same wave again and again, so I would be perceiving it. But let's say while it was emitting a wave, it moves ahead of me, then the first wave front, or let's say, the wave looks like this, right? Like it has ups and downs, as you can see in the image as well. So let's say I received the first up at 1 second, and as it has moved forward, the wave also gets stretched a bit, right? Because the wave is also dependent on the source. So the wave also gets stretched a bit. And because of that, I'm not receiving the second peak at another second. Because it's traveling a larger distance, it'll take more time for the wave to reach me as well, right? Because distance is inversely proportional to time. Because the wave itself is not changing its velocity. So it would take it longer than 1 second to actually reach me. And because it'll take it longer than a second to reach me, the time period of the wave is changing. And what depends on the time period? The frequency, right? The frequency can simply be calculated by 1 upon the time period. And the time period is the time frame between two successive peaks of a wave. So as I'm receiving the peaks not at a constant rate, but because of the stretching of the wave, the time that the wave is taking to reach me is increasing. The time period of the wave is increasing. And because the time period is increasing, the frequency would be decreasing, right? And that's simply what the Doppler effect is. So if something is moving away from you, you would see the frequency of the particular wave that you're receiving getting lower, because it's taking a longer time to reach you. And if something is moving, and if the object producing the sound, in this case the bike horn, if it's moving towards me, I would be perceiving its frequency as getting higher and higher because it's taking less and less time to actually reach me. That's why you can observe the next time you hear a bike passing by you, that when it's coming towards you, it it like its pitch would be increasing, and when it comes to you, like when it's at the same position as you, when there's not much of a distance between you and the bike, that it would reach its peak, and after that the frequency would start decreasing again, so the pitch would get lower. So that's what the Doppler effect is. It's not something very complicated. It's something that we can observe just anywhere, not only in space but on Earth as well. In a train is, I think a train is the best. When I'm traveling on a train, that's the thing that I like to do the most, is listening for Doppler effects. It feels very good. So yeah, the Doppler effect is a property that's not exclusive to sound waves. It happens to any sort of waves. And because light is also a wave, it goes without saying that light would also be undergoing the Doppler effect, right? But then you would ask that why do we not see it happening every day, right? Let's say if there's a car going in front of you, the car's backlight would also be emitting light, right? So you might ask that if the car is going away from me, then why am I not observing the color of the color of the backlight changing? Because the source of the wave is also changing, right? So I should be observing it, and that's a very good question. The thing is, in light, the frequency of at least the visible light is very, very, very low, right? So when we're talking about sound waves, the frequency is very much higher than the frequency of light waves. So in order for a Doppler effect to actually be observable when we're talking about light waves, the distance needs to be very, very big for the Doppler effect to actually take place. Luckily for us, we have just the right place to observe that, the universe, right? Because the universe is huge and things are constantly moving. So that's a great place where you can actually observe redshifts. And observing redshifts is actually what got us to thinking about the expansion of the universe and dark energy. So I'll talk more about that right now. Before I go on, I hope everyone has understood what the Doppler effect is, because that will be crucial in understanding redshift as well. So if anyone has any questions, just feel free to ask. Yeah, Tisha, go ahead.
Yeah, sorry. I just wanted to say that I'm sorry I joined late. Can you just explain, like in a short and crisp way, about Doppler effects, because I didn't really understand it.
All right, sure. So I'll be brief because we don't have a lot of time, but I hope you can understand this. That the Doppler effect is basically an effect that's exclusive to waves. So whenever something producing a wave is moving either away from you or towards you, the time that it takes for the wave from that object to reach you is also changing. So if something is moving towards me, it'll take the wave less time to reach me. And if something is moving away from me, it would take the wave emitted by that object to take longer to reach me, right? And because it's taking longer to reach me, its frequency would be shorter. And if it's taking a shorter time to reach me, its frequency would be higher, because frequency is inversely dependent on time. And that's basically what the Doppler effect is: the change of frequency of an observed wave when the source emitting the wave is either moving towards you or away from you. So I hope you got a general idea from that.
Yes. Thank you.
All right, no problem. I hope nobody has any questions on Doppler effect. So I'll talk about redshifts now. So one thing that I want to first highlight is the Hubble constant. So as Devangi also mentioned earlier, that the universe is constantly expanding, right? And there was this scientist named Edwin Hubble who actually discovered this phenomenon, who actually came up with the idea of the universe being expansive. And he came up with this constant value known as the Hubble constant, which basically defined the rate at which the universe is expanding. So that was the general idea that everyone had, that the universe is expanding at a fixed rate, and that rate was defined by the Hubble constant. But later on, when we observed more things, we figured out that the universe is actually not expanding at a fixed speed, it's actually expanding at different rates. It's accelerating. The expansion of the universe is actually accelerating. That's why the value of the Hubble constant also keeps changing. So I'll talk more about this in detail, but that's the general idea that I wanted to have. So Devangi, can you move to the next slide, please? Thank you. So let's talk about redshifts now. So redshift are just a simple specific subset of Doppler effects, right? So the Doppler effect is a broader term that is used to define changes in frequency of any moving object. But redshifts is more of a, sorry about that. Redshifts are more cosmological. It's a specifically cosmological term where we're talking about the Doppler effect taking place in the universe on a cosmic scale. So as I mentioned earlier, you won't be observing the Doppler effect in the tail light of a car moving away from you, because the frequency of the light is the wavelength of the light is very, very small. So you won't be able to observe the Doppler effect actually taking place, because we need the object to be moving across huge distances to actually observe the redshift. So that's one idea that astrophysicists had, that let's observe how the frequency emitted by stars is actually changing through time, and let's and based on that, let's try to figure out the size of the universe, the expansion of the universe, the age of the universe, and so on. So that's the first idea that they had. So back in the early 1900s or the mid 1900s, that's what Edwin Hubble did. He observed the redshifts of a few galaxies, of a few stars, galaxies, sorry, where he saw that when he observed the galaxy on a particular day, the galaxy would have a particular wavelength, right, a particular frequency. But if the same galaxy was observed some fixed duration of time later, he observed that the frequency had actually changed. It had become more red. And becoming more red basically means that you have an electromagnetic spectrum, right? You must have heard Vibgyor, the term. So when you're talking about observable light, on one end we have violet light, and on the other end we have red light, right? So when we talk about redshift, we're saying that as the frequency of the waves that are emitted by the star is increasing, because the star, or the galaxy in this case, is moving farther away from us, the frequency would be getting lower, and the observable color of the galaxy would start shifting towards the red side of the observable spectrum, right? And that's what redshift is. So that's why we call it a redshift, because ideally, if it completely moves towards the right side, then the galaxy would appear to be red than it was earlier. So that's what the redshift is. So that's what Edwin Hubble did. He observed galaxies, and he found that the frequency of the wavelength that he was receiving from those galaxies were decreasing over a set period of time. Based on that, he figured out that these galaxies are moving away from us, right? Now, there can be a lot of explanations about why a galaxy would be moving away from us, right? The universe is expanding isn't usually the first idea that we have. So what Edwin Hubble did further was that he studied whether there's something actually acting on the galaxies gravitationally. So is there something on the other side that's pulling the galaxies away from us? And the surprising answer was no. There was not. There was not anything that is gravitationally pulling the galaxies away from us. And the other shocking observation was that this particular observation wasn't special to a particular direction or particular point in space. Every galaxy that we observed in a similar way produced similar results. So it wasn't possible that everything is getting pulled away from us based on gravity, right? He observed that there is something. This increase in distance is happening on its own, which is when we came up with the idea that the universe is actually expanding. So more space is being created between us and those galaxies, which is why the distance between us and that galaxy is increasing, and that's why these galaxies are getting redshifted. So that's one thing that we came up with, that based on redshifts, we figured out that the universe is actually expanding. But there was something more shocking in store for physicists. So the idea that the universe is expanding was something that had been accepted by all of us, and it was something that wasn't very tough to understand. But more recently, we found out that those redshifts aren't linear. And what I mean by that is that if something was, uh, let's say I take this thing, it's supposed to be a moon lamp and it's not emitting any light as well. So you're going to have to bear with me. But let's say if this moon is moving away from you at a fixed speed, then the redshift that you perceive, so the amount by which the wavelength of this moon would be changing for you, would also be following a linear fashion, right? And by linear, I mean something that's predictable. On a graph, it would come as a straight line. But surprisingly, that was not what was happening. We observed that uh, the redshift was actually following an exponential scale. So if we go back to classical mechanics for just a second, we see that if a car is moving at, let's say, 10 meters per second, then the distance versus time graph would be a straight line, right? It would be a linear graph. But if it's accelerating, so if the driver puts his foot on the accelerator, then more distance would be covered by the car each successive second, right? That's what acceleration is. So we would get an exponential graph. And a similar thing was observed for redshifts as well, that instead of the galaxies, or in this case, we were observing supernovae. So that's one topic that we've covered earlier as well. So some scientists were studying supernovae, and what they observed was that instead of the amount by which the supernovae get redshifted being linear, we observed that the change was actually exponential, which told us that the expanse of the universe is not happening at a fixed rate. It's actually accelerating. So this universe is actually expanding at a faster rate each second, which was surprising to everyone. So nobody could understand it. And that's one other thing that Redshift allowed us to discover, that not only is the universe expanding, but the expansion of the universe is also accelerated. Can we move to the next slide? Thank you. So that's one thing that we discovered, that the universe is not expanding linearly. It's actually expanding at an exponential scale. So the next question was why? Why is the universe expanding? Why is the expansion of the universe accelerating? So the first why would have been, why is the universe expanding in the first place? And that answer was covered by the Big Bang Theory, which I think we've covered in previous sessions. So that answer we were mostly comfortable with, that the universe is expanding. That's because the universe has been expanding ever since it was born, right? But the next question was, we get that the universe is expanding, but why is this expansion being accelerated? Which is where the idea of dark energy actually comes in. So I'll try to explain this with a very simple method, that if you go back to, again, Newtonian mechanics, you are familiar with the expression F is equal to ma, or force is equal to mass times the acceleration. So if something is accelerating across a given distance, then there must be some force being applied on that object that would cause it to accelerate, right? So let's say if this ball is moving at a fixed speed, and let's ignore friction, let's say if friction is not existing, then in order for me to get it to move faster, I would have to push it, right? So that's what F is equal to ma is, that in order to accelerate something, we must provide some sort of a force. And force is also proportional to energy, right? So if in order to move something at a faster rate, we must provide some amount of energy. And that's the question that we had, that if the universe's expansion is accelerating, where is the universe getting the energy from? How does the universe have the energy to actually expand the universe? And that's where the idea of dark energy came in. That in order for the expansion of the universe to be accelerated, it needs some mysterious source of energy, and we call that mysterious source of energy dark energy. That's why the name dark energy. Next slide, please. So Let's then talk about the cosmological constant. So we briefly mentioned the cosmological constant in the video as well. So what the cosmological constant is, it's basically a theoretical explanation of what dark energy is. So because dark energy is such an obscure concept, it's a concept that none of us actually know about, there are different explanations about what it is. And the cosmological constant is a very popular explanation. So it was first introduced by Albert Einstein when he was working on the theory of general relativity. He gave the cosmological constant as a constant that would explain why the universe is static. So I think Devangi also mentioned that earlier. That the idea that Einstein had was that the universe is static; it exists in a static manner; it's not changing. And the cosmological constant is the constant value that allows the universe to prevent uh, collapsing into itself because of gravity. But back then, Edwin Hubble then came up with the idea that the universe is actually expanding, and the cosmological constant was then trashed because it made no sense, right? If the universe is expanding, it could not be static anymore, right? I think I made a typo there. It's not supposed to be status, it's supposed to be static. So that's the first mention of the cosmological constant, but Albert Einstein did not incorporate it into the general theory of relativity because it did not make sense anymore because we knew that the universe is expanding. But then we found out that not only is the universe expanding, but it's also accelerating in its expansion, right? Which is when the cosmological constant made a comeback. So I'll simplify this a bit for you that the cosmological constant in the eyes of Einstein was basically a parameter that was allowing the universe to resist the gravitational force from collapsing itself, collapsing the universe into itself because of gravity. Now, if we sort of modify the cosmological constant to think about the constant not being a source by which it's preventing itself from collapsing into itself, but as a force that's actually producing the opposite effect, which is instead of preventing it from being pulled into itself, it's actually allowing the universe to exert more force in other directions. That would explain what dark energy is to a large extent, right? Because dark energy, as we talked about, is only talking about how the universe is actually expanding at an accelerated rate. So what's causing the acceleration? Which is why the cosmological constant gives us a rough explanation of what dark energy could be in mathematical terms. So if you're interested in this topic, you can read more about it. I presented it to you in a simplified manner because it's a bit complicated, and it's only one of the many explanations of dark energy. So can we move to the last slide? Yeah. So the last thing that I wanted to mention was to address a very common concern or a very common doubt that a lot of people have. How are dark energy and dark matter connected? Are these two things the same? And the answer is no. Dark energy and dark matter are not the same at all. So don't get that idea in your head. The only reason why they have the same first name, which is dark, is because we don't know anything about them. So as we've repeatedly encountered in the past, physicists are not very good at naming things. They tend to bungle things up, and they aren't very good at the job of naming the things that they theorize or discover. So the reason why we call dark matter dark and dark energy dark is because we don't know anything about them. So we call them dark, but they aren't actually connected. The only connection, or not a connection, but the only similarity that they have is in terms of the composition of the universe. So when we talk about the universe being composed of matter, we can talk about baryonic matter, as Pantha discussed earlier. We can talk about dark matter, and we can also talk about dark energy here, because there's a principle in physics known as energy mass equivalence, which was given by Einstein through the famous equation E equals mc squared, which basically says that energy and mass are actually interrelated. And that's something we have discussed briefly in the past as well, that mass and energy can actually be equated using this particular equation. So because dark energy is a form of energy, we can also call it a form of matter or a form of mass, right? Because matter is anything that has mass. And which is why we can come up with the idea that a large chunk of the universe is actually composed of dark energy. As Devangi mentioned earlier, based on our calculations, 68% of everything in the universe is made up of dark energy. So that's much, much, much more than the majority of the of what we know, right? So 68% comes from dark energy, 26% comes from dark matter, and only 5% comes from things that we actually know. So the stuff that I'm made of, this phone is made of, this laptop that I'm using is made of, only accounts for about 5% of everything that's composed of everything that we know from the standard model and baryonic pattern. The rest of us is, as the name suggests, dark. So it's something that we aren't very well aware about. So that's it from my end on dark energy. I hope you had an understanding.
Uday, before we go forward, because Madhav has raised hand for asking some question, I would like to take privilege to welcome Dr. Arindam and Dr. Kenji here. Will request to switch off this share mode, and because the wind up time was 7:10, so I requested them here to be for few minutes because they are very busy. We will continue for another 10 minutes, but before that, would like to listen from Dr. Rindam and Dr. Kinji about the sessions. It will be very nice because students are there, and the first session which was taken by you, and uh, obviously Uday, Devangi, and Pantho were there in that. So it was a great success, and you see the result. I can vouch that these 16, so 14, 15, 16, actually there were 20 students. Some of them will be definitely be taking physics and taking pure science. The whole idea was this only. So over to you, Dr. Kenji and Dr. Arindam. Thank you. And in the meantime, can I request most of the students who are attending here to switch on this video, because would like to take a photograph with Dr. Arindam and Dr. Kenji, including Uday and Rachna ma'am. Thank you. So may I request Dr. Kenji to speak first, and followed by 2 lines for Dr. Arindam. Thank you.
Yeah, so of course, I'm sorry that I only attend a limited part of this lectures, but yeah, but such activity would be helpful for, especially for the high energy undergraduate students, and to know some key points of the, for example, astroparticle physics. Yeah, to motivate them and provide some introductory information of them. This is sounds meaningful for such persons. Yeah.
Dr. Kenji, are you satisfied with these 3 sets of your students, Pantho and Devangi from SNU and Uday from IB 13, already graduated from SNS? Are you satisfied with the way they took this 1.5 month session?
This is a question for me?
Yes.
Yeah, so maybe they are very interested in particle physics and astroparticle physics. Yeah, so probably they have learned some basics of them, and this is very nice.
So children, do you have any question? Urjit, the students, those who are attending the session, would you like to speak something about this session, and to Dr. Kenji and Dr. Arindam? Over to you, Urjit, any one of you, those who are attending the session right from the first to till now. I think you are on mute. If you are taking, Urjit, you are speaking.
Ma'am, I really don't have any questions right now. All my questions were addressed.
Okay. So over to you, Pantho. You can welcome Dr. Arindam too. And because I don't know how much more time the session will take, according to my understanding, it may take another 10-15 minutes. So you should invite now Dr. Arindam also and take his view. And then if it's their wish, if they want to stay or they can leave because they are busy people, and you can continue your session. We would also like to thank all the audience, and most important person in this is Rachna ma'am, who was always there with these three kids. Over to you, Pantho.
Thank you, ma'am. So, Dr. Arindam, sir, would you like to say something regarding this?
Well, I really don't know what to say. You guys have done a good job, I believe. Yeah, yeah. Thanks for spreading the excitement, and I hope
Thank you, sir.
some
Thank you,
of the
sir.
younger people would also take up basic science and yeah, and just have fun and
We
yeah,
the
learning and thinking about it. That's it. Thank you. Thank you for the initiative.
uh, Rachna ma'am,
Yeah,
would you like
yes,
to
ma'am.
speak
Yeah.
and please
Yes,
convey
ma'am.
your thanks
Yeah,
to.
yeah, absolutely. I've got a little network issue, so my video keeps switching on and off. But otherwise, Dr. Kenji and Dr. Arindam and Vinita, ma'am, now you have given such a beautiful opportunity, such a wonderful platform to all of us. I guess while Dr. Kenji and Dr. Arindam were the one who introduced us to this topic, now particle physics is not something which in CBSE we do. Even as teachers, I know there is so much that I don't know. Now, through this platform, we got an opportunity to learn more. And I guess these are three gems of Shiv Nadar institution. We have Pantho, Divangi, and Uday. And I guess they are literally the flag bearers of how students should be. I admire these children the way they've taken it forward. I guess every session, like the rest of us, Urjit, Arnav, Vidush, we are sitting there and we are listening. And I am one of these children. I'm on this side, and they are the ones who are leading the session. The kind of patience that they have shown, the kind of sometimes I used to tell them, at least complete your sentence and then address the questions. But these children have exhibited like infinite patience. So, children, thank you. Most of all, Vinita ma'am, thank you for this platform. Dr. Kenchi, Dr. Arindam, I know you were not a part of every session, but you were virtually part of every session. Because whenever we've designed something, we always, maybe you will come to the session and, we have to do justice to what you have begun. So thank you very much. You have literally affected, influenced, or in a positive way, all of us by your first session and through the series that we have had. So thank you very much. And thank you, children. You are the heroes. Real to chodo, you are the heroes of whatever has happened. Really, really admire what you've done and all the best always and loads of blessings. Now I'm older, so I can give you blessings also. So thank you.
Over to you, Panthu. You can continue the session. And as and when they feel Dr. Arindam and Dr. Kenji can leave, yes, there are no words to say thanks to these two professors who took time, and the sessions were moderated in the beginning, and thanks a lot. Over to you, Panthu.
Thank you, ma'am. So, Devangi, can you? Yeah, thanks. Okay, so before this, I remember Madhav had a question, right?
Yeah, I wanted to ask that how did we know that how many percentage of dark matter and dark energy we have? How did we detect that? Hello?
Hello?
Yeah,
Am I audible?
Yeah.
yeah. Could you repeat the last bit of your question, please?
I said that how did we get that there is so much dark energy and 30% dark matter and only 5% matter?
Okay, that's a good question. And to be honest, I don't have a very clear answer to that. Yeah, we know that like there's a field of physics known as experimental physics, which uh, in which scientists are basically involved in conducting experiments, and these values have been experimentally calculated. So, as Pant also mentioned earlier, that we know that dark matter exists because we observe things such as galaxy spin and gravitational lensing and so on, which are phenomena that directly reflect on the mass of those galaxies and how much gravitational force is being exerted by them, and we can sort of backtrack them and do the math to get a rough idea about how much dark matter there is in the universe. And when it comes to dark energy, what we basically do is that in dark energy, for dark energy, we're calculating a magnitude for energy, right? And energy is a scalar property in which, in this particular case, which is causing the acceleration of the expansion of the universe, right? So what we can basically do is, using the redshift that I talked about, we can get a general idea about how much the universe's expansion is being accelerated. So we can get some mathematical idea about how much acceleration is actually taking place. And based on that acceleration, we can do the math and try to figure out how much energy there is, how much energy there must be for there to be the acceleration of that particular magnitude. And based on that, we can calculate, or not calculate, but at least get a rough estimate about how much dark energy there is in the universe. So I don't think these values are super precise. These are estimates, but I think that's a general methodology that we must have followed to do that.
And also there are a lot of new models which like are confused, that are saying that maybe that 70% is not entirely dark matter only. Yes, sir. Would you like to answer this question?
I would just like to add a comment that into your question, that how do we measure, how do we know that there is about 60%, 68% or about 70% of dark energy, uh, and about 26% of dark matter. So there is this, the most precise, there are various evidences both for dark energy in and dark matter across various length scales for dark matter in particular in cosmology. But this particular measurement that I think Uday was quoting, the most precise one is from cosmic microwave background radiation. So this is kind of the oldest light that we can see from a very, very, very early universe. So our universe is about 14 billion years old. That's to the best of our knowledge. And this light is, it started about uh, when the universe was about 4 lakh 0.4 million years old, and since then it's kind of free streaming to us. This photon light, that carries a plethora of information, and so this happens to be isotropic in from all directions. So what they do is they send satellites to space to accurately see the flux of photons, and it's isotropic. It has a black body temperature distribution of about 2.73 Kelvin, and there is a small delta T over T, about an isotropy of the order of 10 power minus 4 or so. So the point is that this very old light carries an old picture of the universe. From that, it is possible to actually infer how much of dark matter and how much of dark energy would be there. So it's like, light scattering, photons scattering you, and if they are unobstructed, photon scatters you, on you, and it carries an image of you, right? And it's not scattering in between anything, on anything, and it is just propagating. And many years later, if someone can catch that photon, it will be still an image of you. The same principle you use to take a photograph, but of course, a photograph is almost, it appears as instantaneous, because that object is there and photon is coming from that object to your camera, these days camera processor chip, right? And it is carrying an image of the object and then making an imprint about the same thing, but it's on it. So this is the oldest light that we have. This itself is a very fascinating field. So I just wanted to add that. You could read about it, cosmic microwave background radiation. Thank you. That's a fun. Thank you.
Thank you so much, sir, for answering the question. Madhav, is that okay?
Yeah, thank
Okay,
you.
cool. So we would.
Can I just add one line?
Yes, ma'am.
Yeah.
So Dr. Arindam has explained it well. Also, we would expect these students, and especially the one who has asked this question, to further research. And according to your understanding, if you want to speak someday to us, we will arrange a meeting again. And all these queries and what is your understanding. So all of you are encouraged to do further research on this. And if you feel, you can write a mail to Panto, Uday, or Devangi. We can have one more last session, maybe after 15, 20 days or a month after research, and we can sit again, and what you have understood, you should explain. So that is very important. Over to you, Panto. Thank you.
Thank you, ma'am. So we would like to end this whole session with this one slide which highlights the questions that remain. We have talked about a lot of things, but we have also talked about some questions which nobody has answers to. We don't, at least. So these questions are here in the slide. What is dark matter, dark energy? They are shrouded in mystery. What happens inside the event horizon of a black hole? Is the standard model complete? Where does gravity fit in the standard model? Does it not have any counterpart in the standard model? And is Einstein's general relativity is the best case of gravity? What exactly was the Big Bang and what happened during or before that? So and again, where is all the antimatter? This question has popped out a lot of times during our sessions. It's just we don't know where all the antimatter is, and is there a better model than the standard model? So and many more. Obviously, like I could not put all the questions that are unanswered in science, and if I could summarize those questions, where the science would not have been fun. So there are many more questions, and I would request everyone to do your own research. Like just search these up, and you'll easily tumble down a rabbit hole and find new things. Like during this session, I read about some things that I did not know. Yes, sir.
I think forgot to.
There are two hands raised. There is another teacher.
Tisha, you wanna say something?
Yeah, I just had a question. It's not related to this, but I was just wondering, like, what happens to the chemical structure of a water molecule when it changes state? I was just curious to know.
Okay, when a water molecule changes its state, the water molecule, basically the distances between the two water molecule increases. For example, in solid, in ice, water molecules are very tightly packed. Like they're like this, very tightly packed. Like for example, in a cup, they're very tightly packed. You can't change any kind of, you can't push it and like change its dimensions. That is your ice. The water molecules are very tightly packed. But when it turns into water, these molecules have like the intermolecular spaces between the water molecules, it increases, but it does not increase so much that like the molecules, they just start flying out. That happens in gas. In liquid, it increases to a point that they don't, like, they still exert forces on each other, but they don't clump together each. So they have enough kinetic energy, that is heat and movement, that they move around and can stay away from each other. And in case of gases, these kinetic energy, they are so high that they escape out of each other. So there's no, like, the molecules, they don't attract the other molecule anymore.
I think, Panthu, we can share the quiz now, and then the question answer session can go on
I just
simultaneously.
had one thing that I wanted to add that like fits right in with the slide that's currently shared right now. So if any of you are genuinely curious about these questions, I would definitely recommend reading this book. It's called "We Have No Idea." So that's just to play on how, as humans, we think of us as the best species on the earth, and we think that we have figured everything out, right? But as the slide on the screen suggests, there are so many questions that we have no idea about right now. We don't know what dark matter and energy are, and we don't know answers to a lot of these questions. So it's this long book which basically talks about how we as humans actually don't have any idea about what the universe actually is. We've just scratched the surface of science. So if you guys are interested in reading more about what scientists are researching on right now, what questions they're trying to figure out, I would definitely recommend this book. It's not only interesting, but it's written in a very, very funny way. and it's a very entertaining but a very informative read. So yeah, if you want to continue your journey from here, you can